So today we're going to be looking at forces. Okay, so we've got three forces, F1, F2, F3, that are acting on a ball as shown in the vector force diagram. The three forces are described by these following vectors. So really what that means is, for our first vector, F1, that force there, you've got an I and a J component. So, now your I component is positive, which is this axis, and your J component is negative, which is that axis. So we've got one vector going down like that. That's why this one's going in that direction. So this is the force of F1, and it has a length of -5 in the J and a length of 4 in the I component. Now you can do that with all three of them, and you end up with a diagram like this. Now when we're asked to determine the resultant force R, the sum of the three forces F1, F2, F3, it's telling you exactly what to do. So for that first one, to determine the resultant force, R is equal to F1 plus F2 plus F3. Now, if I'm thinking about what this looks like graphically, over here I've gone tail to nose for all three of my vectors, and I'm left with this resultant force here. So that's kind of like the force that's remaining on the ball. Now, it's saying here that there is a resultant force. This is different if we just let the resultant force equal 0. So all I have to do is add together my I components and add together the J components. So I add all of these together, and that gives me 4 plus 10 is 14 minus 6 is 8I. Now I'm going to add together the J component. Now, be careful that you need to take the sign in front. So -5, let's add together first. So 9 minus 5 makes 4. So plus 4J. So this is the resultant vector. So it's going this way, 8, and then it's going up 4. So the resultant vector that's made looks like this. Okay, which is why over here you can see that resultant vector is travelling in that same direction. Now, if we want to determine the magnitude of the resultant vector, all I have to do is do the same magnitude that I always do. So I'm going to calculate the magnitude of our R, which is 8 squared plus 4 squared. So 8 squared is, I'm just going to pop this in the calculator. 8 squared plus 4 squared is 80, and then the square root of 80 is 4 root 5. Now, I'm going to leave it in Sertle form because I like it when things are exact. So that is the Newton force that is acting at the moment. That's what the magnitude means. Now we're going to determine the angle that it makes. So C, the angle. Okay, so in order to calculate the angle, I'm going to use what I know from vectors originally, or you can think about it in terms of what we know about calculating arguments for things as well. So I always do, this is the formula that I normally use, tan theta equals y over x. Okay, now in this we've got the real, wrong thing. We've got the j axis over the I axis. So theta is going to equal 4 over 8 tan inverse 1, which is like, let's chuck that in the calculator, inverse tan of a half. So theta equals 26.56 degrees. Now, I want you to think about this in what we're actually finding. Whenever I use this formula, that's like me saying, oh, that line wasn't very good. Okay, if this is my, I'll do it in a different colour. Let's say this blue is my vector. Whee! Okay, and like that. Okay, so that's the line that I've got. The black is the axis. The angle that this formula will give me is always the angle from the x-axis to the line. Okay, so because my angle is in here, I can say that the angle is actually 26.56. If it was over in this one, I'd have to do 180 minus the angle to find what that is from there to there. But anyway, let's go on to the next part. Determine the angle that the vector, we did that. so the force, F1, is changed so that R equals 0. What is the resultant force that equals 0? Determine the force of F1. All right, so I'm going to rub some stuff out to make some space. Okay, so now we know that R equals 0. And R is F1 plus F2 plus F3. So 0 is equal to, now we're not sure what F1 is, so I'm going to write that as xi plus yj plus this next one, 10i plus 2j minus 6i plus 7j. So because we no longer know what F1 is, we've left it in its component form and we're going to work it out. So I'm going to do this by grouping together my like terms. This, remember to take the sign in front. So now I can split it up into 0 is supposed to be equal to xi plus 10i minus 6j. When I simplify this, I end up with xi is equal to 4i, or 0. And now I'm going to take this one to the other side. So our x component is equal to negative 4i if our resultant force is going to be 0. Now we're going to do the same thing with our j component. So we're going to group our like terms, making sure we take the symbol in front, let them equal 0, and determine what that y is that's remaining. So yj plus 2j plus 7j equals yj plus 9j. And then I'm going to take the 9 to the other side, so yi is equal to 9j. That means that the force of F1, that should be a negative, is equal to minus 4i minus 9j. Okay, so this is included to help you build the idea that each force is made up of an I component and a j component. Now, all of this stuff is just about angles. It's not particularly hard, but it is super fun. So now we're going to look at our next one. Worked example 6. 3 forces A, B, and C act on an object such that the resultant force is 0. The force of A acts at an angle of 150 degrees to force B. They have the same magnitude of 20 newtons. Determine the magnitude of C, calculate the angle and the force C makes with B to the nearest degree. Okay, we're going to start by drawing our diagram. So, the resultant force is equal to 0. Now, that part is important because force is normally equal to mass by acceleration. So when we're saying our resultant force is equal to 0, we're really saying that the acceleration is equal to 0, which means that either this thing is at rest or not moving. Or the other option for the acceleration to be 0 is it's moving with a constant speed. Now, this is something that we really build on in methods in the coming months, and it becomes quite important for us in Year 12. Okay, so resultant force equals 0. The force A acts at an angle of 150 degrees to force B. So I'm going to do this one straight in the air. It doesn't matter where you start. The only thing that matters is that the angle in here is 150 degrees. This one is A, this is B, so C is going to be somewhere over here. Now, if you do this in a different way, if you do A, B, your angle in here is 150, it won't have any effect. Okay, so next thing, A and B both have a magnitude of 20 newtons. Determine the magnitude of C. Okay, so first thing we have to do is we have to work out what the force of C is, or we have to work out what the vector of C is. So we're going to work out all of our vectors. Okay, so A is going straight in the air, and it's got a 20 Newton force. Now, if I think about drawing A like this on its own, it's only got a j component. Now, that length of the j component is 20 because it's going straight up in the air. We don't need to work anything out for that one. So 20j is our a component, or is our a vector. Now we're going to start looking at this vector going down here. So if I draw that vector, there's my axis. I have to work out what angle we're making with the x-axis. So if that was 150 and I want to work out this angle in here, I can do 150 minus 90, and that gives me 60 degrees. So the angle in here is 60 degrees. Now, it's got a length of 20 newtons. Next thing we want to do is we want to start breaking it down into its component form. So I'm going to do this using SOHCAHTOA. Now my I vector is going in this direction and it is adjacent to the angle. My other angle, or my other vector, is opposite. So using SOHCAHTOA, we can work out that to find the length of this line, which is going to make up our I component, I can do, it's A, so it's going to be, I've got A and I've got H, so I'm going to use cos. So cos theta equals adjacent over hypotenuse, and now I can substitute stuff in. Cos of 60 is equal to the adjacent side, which is the part we don't know, divided by 20. Now I can take this 20 across by multiplying, which gets rid of it from here. I'm left with A equals 20 cos of 60. Now, this same algebra step happens all the time. So we can start looking at, whenever I'm looking for a length that is the adjacent side, I can do the hypotenuse times cos of the angle. Okay, and when I chuck that in the calculator, the A component for this is going to be 20 cos 60 degrees. Now, make sure your calculator's in degrees, because if you've been playing in your revision mode, it'll probably be in radians for when we do trig. Okay, so that's 10i. Okay, so this B vector has 10i for this part that makes up the vector, and the other part of the vector is made up by our other trig ratio. So now I've got the opposite side and the hypotenuse side. So to work out this one, I'm going to have to do sine theta equals opposite over hypotenuse. Now, I know I'm going to be looking for the opposite side again, so I can take that hypotenuse up over here straight away and work out that my opposite side is equal to 20 sine 60, which is going to give me, sine 60 is root 3 on 2. So it'll be equal to 20 times root 3 on 2. They will cancel to give me 10. So it's plus 10 root 3j. Now, the other thing I have to consider here is the direction of my vectors. Okay, your trigonometric ratios will only help you work out their lengths. They won't help you work out direction. So this first one is travelling up, meaning it's moving in the positive direction. So this is a positive 20j. For this one, we're travelling in the positive x direction, so our 10 is positive. But now for our other one, we're going down, meaning that this should be a negative because it's going down. So be careful when you're stating your vectors, because one of the biggest mistakes that we find is people put the wrong symbol in front and then those errors carry forward. Okay, so we've worked out A, we've worked out B. Now we can start to work out C, because we know that this has a resultant force of 0. Now what that really means is that the resultant force equals 0, which means that when I add together all of our vectors, it should equal 0. So we're trying to work out this. Okay, so all I have to do is the same steps from before. I'm going to be grouping my I components together and letting them equal 0. So 0 equals xi plus 10i, so xi equals 10i. Then we're going to group together our y components. This. So it's all going to equal 0. 0 equals 20j minus 10 root 3j plus yj. That should be a j. So now I'm going to move all of this to the other side because I can't simplify it because of that third. If I want to convert it to decimals, I can definitely simplify it. So that's going to leave me with yj is equal to 10 root 3 minus 20j. Okay, and then that's the vector that I'm going to use. Now I'm putting that in brackets so I only have to state one j component. This will help me when I have to work out the magnitude of C. So let's start doing the magnitude now that I've worked out all of that part. Once you get used to doing this, you can do it really quickly. It's taken me a long time today because I've explained all of these steps, but normally I wouldn't bother drawing the diagram. I would jump straight to this. As soon as I see I'm calculating an adjacent side, throw it in that formula. As soon as I'm calculating the opposite side, throw it in that formula. Okay, so let's determine the magnitude. So magnitude is just going to be, not the resultant vector, squaring our C vector, which means I'm going to do 10 squared plus 10 root 3 minus 20 squared. You can do this algebraically if you are feeling so inclined, but I'm going to be chucking it straight in the calculator to save myself some time. And that will give you 10.35. So what it's really saying is the force that's exerted along this C vector is 10.35 newtons of force. Okay, and if I want to break it down into component form, then this vector can be expressed as 10I, and then we look for the direction that it's traveling in. Now that'll be minus 10I because it's going backward, and it's going down, so it'll be minus 10 root 3 minus 20j. Okay, so this is the vector of it. I have accounted for the direction that it's traveling here and here. I've used those component forms there. Okay, next thing we're going to do is we're going to calculate the angle that force C makes with B to the nearest degree. Now, again, not hard. You just have to know what you're doing a little bit. We're going to be using my formula again. Tan theta equals your J component over your I component. Now, remember, this is going to give us, here is my axis. It's going to give us the angle in here, okay, which means that I'm going to have to do some other steps later to work out what's going on with the rest of it, but that's the angle that I'm finding. So, theta equals tan inverse 1, our J component, 10 root 3 minus 20 divided by 10. They're both negatives. Chuck that in your calculator. And that's giving me 15 degrees, or it's giving me negative 15 degrees, depending on what you've done. So, now we're going to start looking at my diagram. I know that this angle here is 15 degrees. I know that this angle in here is 60 degrees. I know that the whole thing has to add to 180. So if I want to find the angle that C makes with B, all I have to do is do 180 minus 60 minus 15. And that is going to give me 180 minus 60 minus 15, 105 degrees. Okay, and that's how I work out that stuff. Not hard. Just remember every vector can be broken down into an I and a j component, and then you can use that to find out anything else you want. Next question we're going to do is worked example 11. Now, this is one that talks about frictional forces as well, which means that all we need to do is apply the frictional force formula. Now, that formula is our frictional force is equal to the coefficient of friction multiplied by our normal force. So if I want to find the coefficient of friction, I just do the normal divided by our force. Okay? Not hard. It's actually pretty easy. Now, looking at vectors in the plane always confuses people because we don't take your I and j components as being, these ways like we normally do. We take your I and j components as going I and j. Now, the reason why we do that is because it makes it easier for us when we're resolving our vectors, which means we're breaking it down into our I and j component. Think about it like this. This is the diagram that I've currently got. If I want to get all of these vectors going in the same direction so that I can group my like terms, currently I only have to resolve this one. Okay, which means that I'm going to break it down into a force that's going in the same direction as our normal force and a force that's going in the same direction as our frictional force. So they are parallel to the planes. So that I resolved one force. If I don't do that and I try and break it down into our IJ components being like this, now this force is going in the correct direction, but I need to resolve this force and this force, which means that I would have this force traveling that way, and this force going up and across. Now, if you choose to do it like that, you'll still get the same answer, but this resolves 1, this resolves 2. That's why we do this. Now, it gets a lot more complicated in Year 12 because you start dealing with things where you have force on a plane here, and then it's attached by a tow bar to this force here, and they've both got some sort of weight going down. They've got normal forces going up. They've got forces pulling them this way, and then they've got braking forces going this way. Now, if you choose to ignore the plane and do it this way, that means you're resolving 1, 2, 3, 4, 5, 6 forces opposed to resolving 2. So, do the easy way. Okay, so let's get started. We're going to rub what I've just done on this diagram out. We are going to be writing on the diagram. So a body of mass of 4 kilograms rests on a plane inclined at 30 degrees to the horizontal. So if I didn't have this diagram and I wanted to start from scratch, I'd do this. I've got 30 degrees there. Doesn't matter which direction you draw it in. I've got some object here, and its weight that's going down is 4 times gravity. It's got a normal force going this way and a frictional force going that, a force going that way. Okay, so it is prevented from moving by friction. So the weight, this one here, now to work out that weight force, the resultant vector of the weight force, we just have to square and then square root 4 times gravity. Now, that's going to just give you 4g. Okay, so that's going to be 4 times 9.8. So our force of the weight force is 39.2 newtons. Now, we're going to, the magnitude of the normal reaction. So this is the normal force. Its opposite is going to be this way. Okay, now we're getting this to be in line with these planes. So if this is 30 degrees here, this angle in here is also going to be 30 degrees. Now the reason why that happens If this is 30 degrees and this is a right angle, then this is 60 degrees. Now, if that line that's going up like that is, in the same thing, then this has to add to be 180, meaning this angle in here is 120. If the normal force is acting at 90 degrees, then that means that this is 90 degrees because it's vertically opposite, which means that that is 30 degrees in there too. Now, we do a lot of this in grade 12, and you'll see that this is just always the same here as it is here. Instead of going through the hard work every time and working out all the angles, you can just take it as a fact. Okay, so to work out our normal force, our normal force is going to be equal. Let's do this the other way. So, okay. So we're going to work out this one and we're going to work out this one, okay? So we're going to resolve the W into its two components. So our W vector is made up of, this is our adjacent side and this is our opposite side. This here is our right angle and this is our hypotenuse. So because this is the adjacent, we'll go the I direction first. Now it's traveling opposite to the way we want it to be. So your I component is going to be negative. And then that's going to be negative. It is sine because it's the opposite. The angle is 30 degrees and this is its length. Okay, now for the other one. It's traveling down. That's I. It's traveling down, so it's negative. It is your J component because it's on the what we're using as the Y axis. J. It is going to be cos because it's the adjacent side. So cos 30 degrees, and this is its length, or the hypotenuse. So when I'm resolving my vectors, I just punch that into the calculator, and it's going to tell me what they are. So 39.2 sine 30, negative 19.6 I, minus 33.95J. So that's the vector that makes up. Now, if we're trying to work out our normal force and this thing isn't moving, that means that our resultant force is 0. And then when I group all of my J components together, which is only those two, it's going to have, N is positive because it's traveling in the normal direction. So NJ, sorry. And then I'm subtracting the 33.95J because it's in the opposite direction. Now I can take this to the other side and I'm left with the normal force is equal to 33.95J. Now, I can cut the J off this one because when I'm looking here, the N only has a J component. It doesn't have an I component. Otherwise, we'd have to resolve that one as well. Now, let's look at resolving for our frictional force. So 0 is equal to, now we're looking at grouping all of the ones that go in the X direction. So that's this frictional force here, and that's this force here. Now they're going in opposite directions, which means this one is going to be our positive one because it travels at the same direction as the axis, and this one is going to be our negative one, minus 19.6I. So our frictional force is going to be equal to 19.6I. Now, remember, this one only has an I component, which is why I'm writing it as F with the underline. Okay, so they are the two forces. That's my normal force, that's my frictional force. Now I can work out the coefficient of friction by substituting into this formula or into this formula. Now, this is a formula that you're going to probably get in a question because it's kind of one of those more abstract ones. It's not on the formula sheet. So 19.6 is equal to our coefficient of friction multiplied by 33.95, which means our coefficient of friction is equal to 19.6 divided by 33.95. So it's going to be 19.6 divided by 33.95 gives you 0.577. Now, it doesn't get a unit on the end. This is just like a constant. It's like a multiplier that kind of just tells you what the coefficient of friction is. So it's a coefficient to the frictional force. Ta-da!